Okay, so welcome to the feedback video for Evolution of the Living Earth. This is going to be for part B, so the global environmental change part of the course. Uh, so there we go. So before we crack on, just some general advice for the exam. So I've got a copy here of the front of the exam paper. Now, here are some of the instructions, or here are the instructions for what to do in the exam, how many questions to ask, all that kind of stuff on the left hand side here. Now, the easiest way of failing the exam is, of course, not to follow the instructions, particularly not answering enough questions. So, quite a few people lost a whole bunch of marks because they didn't answer 6 questions. So, the exam has 8 questions. There are 4 sections. There are 2 questions in each section. So you have to answer 1 question from each section. That takes you up to 4 questions, and then there will be a choice. You can answer another additional question from any 2 of the sections. So you're effectively, out of the 8 questions, you're choosing 2 questions not to answer, answering 6 in all. Yeah. So do that. Do read the instructions at the beginning of the exam paper. If there are substantial changes from the format of the exam from previous years, that will usually be communicated to you in advance. So look at the previous year's exam paper for the kind of an idea of what the instruction should be, and kind of prepare yourself for doing that. Then aside from kind of just following the instructions, some more kind of generic advice, and we'll go over some examples of this as we go through the feedback. But quite often people lost marks for not reading the question properly, or misinterpreting the question, and not answering specifically what the question asked. Okay, and just providing an answer which included some information about the general subject area, but didn't address the specific question asked. So do that. It's always worth making sure that you've fully expanded on your answer. So once you've, I guess, provided an answer to all of the questions, well, all 6 of the questions you're answering, do go back and have a look at each part of each question, and just make sure that there aren't kind of places where you could expand on your answer to get more, I guess, towards the higher end of the mark scheme. That would be good. Yeah, so fill in with details kind of once you've provided kind of the bulk of the answer for all of the questions. Okay, so let's just have a look at the mark distribution for the exam. So this is the overall mark for all 4 sections of the exam. So some people did very well, which was great. Some people not so well. Most people did kind of okay. So we'll have a look at each question in turn now, and have a look about where people kind of lost most of the marks. So we're going to look at part B, as I said at the beginning, and first of all, so here are the 2 questions in part B, question 3 and question 4. You can see that question 3 was answered a little better than question 4. Quite a lot of people kind of stumbled a little bit on question 4, and that was largely through not specifically answering the question that was asked. And we'll come on to that when we come to it. But question 3, some very good marks, some very good answers to questions for question 3 from some students, not from others. So this is the question. So it's all about this model, which I was referring to quite a lot in the lectures, of basically a model that describes the surface temperature of the Earth. Okay, and it's split into a number of parts. So the first part, fairly straightforward. What do each of the symbols in this equation represent? I guess I'll show you this mark distribution again, because I forgot I put that in the presentation. But here it is in a slightly wider version. Some good, some okay, some not so good. So don't be a red person. Okay, so back to the question. So what do each of the symbols in this equation represent? So this is fairly straightforward stuff that hopefully will have been repeated a lot in the lectures. So TS is the surface temperature, when saying what all of these things represent, as well as giving the thing that it represents. Also, good idea to give the units, which that might be in. So we've got the surface temperature, the solar flux, the emissivity or absorptivity with the epsilon symbol, alpha is the albedo, and sigma is the Stefan-Boltzmann constant. Okay, so that's kind of stuff. What have got you most of the marks, the questions. Is there any more that you could have expanded on to get maybe some more marks for this question? Well, there are a few things that you could have done here. So, for example, for the albedo, you could have explained a little bit about what albedo actually is. Okay, so albedo is the reflectivity of the planet's surface, and in this case, within this model, it's the albedo of the average of the Earth's surface. So it's a planetary average. That would be in a detail, which should have got you marks. And you could have explained what the Stefan-Boltzmann constant is and what that's related to in terms of the amount of energy emitted from the surface of a black body with temperature. Okay, that kind of stuff. So a simple answer would have just been a list. Slightly better answer would have been a list with some units, and a great answer would have been a list, some units, and a little bit of explanation for some of the parameters. So there you go. That's part A. I think quite a lot of people did mostly okay in this part of the question, which was nice. Okay, moving on to the next part. You can see this is a substantially larger. This part of the question is worth double part A. So expect a little bit more of a substantial answer to this part of the question. So we're looking for examples of processes that have changed the Earth's climate in the past. Explain how each of the variables in the model affects climate. Okay. So we can start to kind of like maybe rewrite that question in our own words if we're doing this as a revision exercise. But just looking at the question itself, I've just highlighted in bold here some of the key words of this question. So if you're maybe a highlighter in your exam, these are the things you might want to highlight in the exam paper. Okay, so we want to see some examples in the answer. The question is asking for some processes. Okay. And it's those processes and examples should operate in the past. So we're looking for examples from the past, not examples that are happening now. And we're asking for how each of the variables affects climate. And we want you to explain that. So you could kind of, I've rewritten this question in kind of another way. So for each variable, and I've been specific about for each variable, how a change in their value will change temperature. Okay, so in this case, I've said that temperature is the climate parameter that we are looking to reconstruct. Okay, or to model. Okay, so give an example, of each one of these things. So we can do that. We'll go through each of the basically the symbols. So I think Stefan-Boltzmann constant. Well, that's a constant. That doesn't change. So it might be worth mentioning that, but not really expanding on it any more than it's a constant. It's not going to change, therefore it doesn't affect climate. Some people, I think, wrote a little bit about temperature changing affecting climate, which is a little bit circular in case the temperature is a part of the description of climate. So that wouldn't have got you too many marks. But looking on now to the solar flux. So if we look at solar flux, this is a combination of how powerful the sun is and how far we are away from the sun. So the stronger, the hotter the sun is, or the closer we are to the sun, the greater the solar flux will be. And then we can look at some examples in the past, how that has changed. And one of the examples we did in one of the lectures was the change in basically the power of the sun through time. So over time, the sun has been getting more and more luminous, more hot, it's bringing out more radiation because it's getting denser. That was explained in the lecture through the process of burning hydrogen, creating helium, and therefore increasing the efficiency of the nuclear reactions in the sun. And that has caused, over time, the Earth to heat up. Should have done. Other examples are changing the distance between the Earth and the Sun, so the so-called Milankovitch orbital variability. Now we'll see here why this is maybe not such a great example, but nonetheless, it will have an effect on the temperature. So when we are closer to the Sun, then uh, the solar flux will be greater, and that should indicate a period of warming. And also, we've had in the past cycles of variability in the power of the sun, so-called sunspot cycles, and they have also potentially had a small effect on the Earth's climate. So when S0 goes up, then the temperature also goes up. So you could have used the equation to kind of explain that in terms of the S0 is the top part of the fraction. So if you increase that term, then you increase the temperature. Although in this case, you wouldn't have got much credit for writing out that equation because it was given in the question. Okay. We can look at the albedo as well. So changing albedo, you should explain what albedo might be. So the lighter the color, the surface of the Earth, the more reflective it is. What kind of processes would change the color of the surface of the Earth? So glaciation, deforestation, desertification. They will change the albedo. And you see that in the equation on the right here, that the albedo is a term on the top of the fraction, but it's 1 minus the albedo. So the bigger the albedo gets, that 1 minus alpha term will get smaller, and therefore the temperature of the surface of the Earth will go down when the albedo is high. So the more reflective the planet, the cooler it is. And you could give a specific example of when this has happened in the past. So you could give many examples of when changes in the Earth's surface color has changed in the past. So you should give an example of that. Last glacial maximum, for instance, would be a good one. Many people used. The emissivity, absorptivity. So that's really looking at the greenhouse gas effect. So the more opaque the atmosphere is to outgoing long wave radiation, the higher the emissivity of the atmosphere is. And we might want to look at times in the past when CO2 levels were higher or lower for whatever reason. Maybe changes in the long-term rate of volcanism, changes in weathering would change the amount of CO2. Would be a good way of expanding on that in terms of the process. So that was part B. Now looking at part C now, again, we're going to go back and have a look at these Milankovitch, these orbital timescale changes in the Earth's climate. And the question really is kind of not really specifically about how these forcings work, but why the model that we've shown here, why this really simple model with just these few parameters, why that model is not suitable for explaining the magnitude of climate change. Okay? So you think about, I guess, writing this question and making it in another way. Really, what I'm really trying to ask here is, what can't the model do? What is missing from the model to allow us to properly kind of reconstruct the climate changes that have occurred due to these orbital or these Milankovitch forces? And if you think about what's the parameter that's changing as we change the orbit of the planet around the sun, the forcing there, the thing that's the variable that's changing is the solar flux. When we've got maybe an more elliptical orbit during one part of the year, we might be further away, so S0 might be lower. When we're closer to the sun during the other part of the year, S0 will be higher. So another way of asking the question might just be this thing at the bottom here. So is S0 here, is the solar flux sufficient to represent the Milankovitch? And I've kind of already hinted at why that might not be in my spiel that I've just given then. In that this model only has a single value for the annual kind of global average of the solar flux. Whereas the orbital forcings don't really change the overall, the average annual forcing. That doesn't really change much with changes in the Earth's orbit. What really does change, though, is the seasonal variability between hemispheres. So it might make um, winters more extreme and summers more extreme. So it might get really cold winter and a warm summer because we have an extremely kind of tilted over axis of rotation. So we get very strong seasons, but the average amount of radiation arriving at the Earth is unchanged. So quite a few people went a little bit astray in this question in that they spent a lot of time explaining what the orbital parameters are and how they vary and what are all of the different kind of parameters of precession and obliquity and eccentricity and all this kind of stuff, which was good that these are things that you know, but they didn't answer the specific question as to why the simple model is unable to reconstruct the magnitudes of change. So this is one of the images from one of the slides from the lectures. And the thing that the orbital forcings kind of are not really on their own able to reconstruct, if I just use the pointer here, is that you can see that we have these changes in forcings, and you can see here this is the northern hemisphere up here and the southern hemisphere down here through time. Here, so we're present is over here. This is 500,000 years ago, and you can see that we have strong seasonality changes as we are changing the kind of the axial tilt of the Earth's kind of rotation, and this doesn't look like the climate that we get from these forces. Okay, we don't get a nice smooth sinusoidal climate signal coming out here. We get this kind of sawtooth, jagged climate response, where the timing of the climate changes seem to match up with the changes in the Earth's orbit, but the amount of change is not kind of directly related to the amount of kind of change in the Earth's orbit. So the thing that's missing is, first of all, that there is a simplification in this climate model that the solar flux is only represented by the annual average, which doesn't really change with orbital forcings. So it doesn't include the changes in seasonality in the solar flux, the changes in the differences between hemispheres, doesn't include any of that. But importantly, also, it doesn't include the climate feedbacks. Okay, so it doesn't include these things where if we have a small change in maybe the amount of ice cover in the northern hemisphere due to some seasonal forcing from orbital change, that will result in a change in the albedo, which might reinforce any initial kind of climate change, leading to an amplification of the initial climate forcing. So what's really missing is the feedbacks in the climate system. So this model here doesn't really have feedbacks. It has the parameters that the feedbacks use, but it doesn't have those feedbacks built into the model. So that's something that would be kind of was required in the answer that would have got you some marks, which was missing in quite a lot of answers. So there we go. So that was question 3. So hopefully, if you were one of these kind of red people down at the suboptimal end of the marking range, you can see now where you might have lost some of the marks, where you might have been kind of led astray by just writing down stuff you knew rather than stuff that was answering the question. So that's a little thing for you there. Right. Okay, so we're going to go straight on and have a look at the other question in part B, question 4. So this question really wasn't answered as well at all as question 3, and again, this was largely because people were not specifically answering the question that was given, and we're going to have a look at that. So again, question with some parts, in this case only 2 parts. So I provided a little graph in the exam paper showing the Earth's average surface temperature over the last century or so, 140 years here. So this is the surface temperature of the Earth through time, and I think one of the I guess the most terrifying graphs of all of climate science, really showing this kind of continuous warming or continuous average warming throughout the 20th century and continuing for the last 20 years, showing kind of the Earth's temperature rising substantially above the pre-industrial kind of average. Now, let's have a look about what the question is actually answering here. Okay, so the first part is asking what evidence do we have that we can attribute long-term trend in the graph to anthropogenic activities. So for this part, it's not really about the graph at all. It's really just saying there's been climate change. We've had a lot of warming over the last 100 years. How do we know that it's our anthropogenic activities and not a natural phenomenon? Okay. So yeah, here's the question again. And quite a lot of people wrote a whole bunch of stuff about that the Earth has increased in temperature and that our anthropogenic activities are responsible for this. But what's really missing in the answers was the evidence. So the question specifically asks for the evidence for the link between the Earth's surface temperature rise and human activities. Yeah, so people wrote quite a lot about the Earth's temperature rise and what effects this was having, which was not the question. They also included some statements about kind of how our industrial activities have changed through time, how we've increased fossil fuel burning through this time. Now that on its own is not evidence that the anthropogenic activities are responsible for the temperature rise. It is part of I guess the logical argument, but just by saying the temperature has gone up and anthropogenic activities have increased and we've burnt more fossil fuels, that doesn't actually prove a link between the two. Okay. So what are the kind of the logical arguments that we can use to prove that recent global warming is not natural and we did it? Okay. So the observation in both of these lines of arguments here is that the global temperature is rising. Okay. And that's kind of shown in the graph and is pretty kind of incontrovertible. And then one line of argument might go down this kind of this top route here. So these that I've like not grayed out now. So one line of argument is that we can show that warming is due to carbon dioxide in the atmosphere and is not caused by something else, changes in the solar output or changes in amounts of volcanism or land use change or anything like that. So it's just due to CO2 in the atmosphere. And that on its own doesn't prove that we've done it. We also need to then go through the next step of the argument that says that the increase of CO2 in the atmosphere is the result of us burning fossil fuels. Okay, so those two things are kind of required. Another kind of line of argument, which is kind of separate to the first one, is that the global temperature is rising, and this has not happened before. So temperature has not risen by this amount or this quickly before. Okay, so that is a line of evidence that's used to show that the warming that we have observed is due to a recent change in the way that the Earth system works. And then you can start to add in the argument that this change coincides with our burning of fossil fuels and our increase in industrial activity. Therefore, because it's anomalous, we can start to tie these two things together. Okay. So looking at the first kind of line of evidence, how do we show that the warming is due to carbon dioxide in the atmosphere and not other forces? So the way that we do this is with climate models. Okay, so we can run climate models of the Earth system, and we can run those through time with natural forcings, and we can then run them again with different amounts of greenhouse gas forcings. We can add different greenhouse gases to the atmosphere, and we have records of how much greenhouse gas is in the atmosphere or was in the atmosphere through time. So we can run a model with that, and the line of evidence that is used is that the observed temperature changes across the globe and also regional temperature changes can only be reconstructed faithfully if we include natural climate forcing changes and also anthropogenic CO2 forces. So another way of saying that is that without including carbon dioxide into our climate models, it is impossible to reconstruct the climate change that we have observed over the 20th century. So that line of evidence suggests that then the warming must be forced, essentially by emission, must be forced by carbon dioxide in the atmosphere. So the next step we need to say is where's that carbon dioxide come from? Is that from us, or is that just some natural thing that's happened? And then this is the point where we can start to look at the observations of CO2 and link those to our accounting of where we know that we have burned a certain amount of fossil fuels by basically writing down when we turned our power stations on, when we made concrete and all that kind of stuff, and accounting for where that carbon has gone. So we know that the carbon dioxide concentration has gone up in the atmosphere, and we have put more than that into the atmosphere from our anthropogenic fossil fuel burning activities. So therefore, the rise in the atmosphere is almost certainly from the carbon that we have burnt. There are other lines of evidence, such as kind of using the isotope ratios of the carbon dioxide in the atmosphere and the amount of radiocarbon in the atmosphere. But those were not really covered in the lecture, so I wouldn't really expect you to go into those in any detail. But really just linking together the observations of CO2 going up and accounting for how much we've actually burnt. Those links together. Okay. We can also, I showed the movie of this this little thingammy-doobry here. We can actually observe the CO2, and this isn't a picture of observations. This is a combination of observations and a climate model. But we can observe the sources of CO2. We can see industrial sources of CO2 and measure the concentrations of the atmosphere near them and show that these are sources of CO2 in the atmosphere and can explain the rise in the atmospheric carbon dioxide concentrations. So both by observations and accounting, we can tie down the origin of the CO2 in the atmosphere to us burning stuff and driving around in fancy pants cars and airplanes and whatnot. Okay, so just briefly, the other line of evidence is that the climate change that we're seeing in the 20th century, that's anomalous. We have not seen such rapid changes in the past. So you could have gone down that route and kind of given some examples of some of maybe the proxy evidence of climate or Earth temperature over the last maybe 2,000 years, and showing that what we're seeing at the moment is really very much different. Okay, so that's another line of evidence a few people gave, got some marks for, which was good. Okay, so the second part of the question, this, and it's worth 70% of the credits. So this is really looking for quite a substantial answer for this. And this is where quite a lot of people missed out a bunch of marks because they didn't I think really grasp what specifically was being asked. So describe the mechanisms. So we're looking for some descriptions of processes and ways that the Earth's climate has changed that are likely responsible for the variability in the Earth's surface temperature on timescales less than 10 years. Okay, so let's have a look at that graph again. So I think where this went a little bit astray for quite a lot of people is that they didn't really grasp this last part of this on variability in the Earth's surface temperature on timescales of less than 10 years. So What we were not really looking for was a description of this overall increase in temperature. That's not what the question was asking. So if you wrote an answer that was all about, burning fossil fuels and increasing the amount of greenhouse gases in the atmosphere and increasing global warming, that's not what the question was asking about. Okay, so if we're looking at the variability, we're looking at these little ups and downs on very short timescales. Okay, some of these lumps lasting a few years, some of them less than a year, zipping up, zipping down. What is causing that kind of, basically what's causing the noise in this climate record? What's causing the high frequency variability? So that's what the question is asking. And I guess the bulk, this is quite a large chunk of credit for a question, 70%. So we're looking for quite a lot of detail in the description of how these potential short-term climate forcings work. Okay. So this is I guess one of the potential forcings. Okay, so the power of the sun kind of goes up and down on a fairly regular 11-year cycle. So we have ups and downs every 5 years of warmer, 5 years of cooler. And that's, if the sun's kind of power is changing, then that should change the Earth's surface temperature. So here is an example of where you could describe a mechanism and of a potential change. And I think a few people did this. But what's really important here is to note that actually we don't really see a huge amount of variability actually on this regular timescale. So if you look at how regular this sunspot cycle is, and if we go back to look at the climate record, there's a hint of a 10-year cycle, 11-year cycle in the climate data, but it's really not very obvious. So one of the things you could have done for some marks is actually said, well, this is a potential mechanism, and it's actually not significantly causing there to be kind of much variability in the Earth's surface temperature. So although the question is asking for likely, okay, because this is quite a large kind of question, you can also, excuse me, use your time to excuse me, use your time to give counter examples as part of the answer to your question of mechanisms which should cause a change, but in this case don't. Other things that we covered in the lecture course that might cause some short-term climate variability are things like volcanic eruptions going off and changing the reflectivity of the atmosphere by adding aerosols or increasing the amount or longevity of aerosols in the atmosphere. So this is the idea that when a large volcano goes off, we should get a bit of a short-term climate cooling, maybe a year or so of climate cooling, depending on where the volcano is, how much sulfur was ejected. So it would be good to have a description of how this works. What is it in the volcano that causes the aerosols to form? What gases are important? What are the chemical changes to those gases? So sulfur dioxide reacts with water to form sulfuric acid. That acts as a cloud condensation nuclei because it's very high boiling point, so it likes to condense into lots and lots of small droplets, which act as a place where water can start condensing. So we form more clouds on these aerosols. Those clouds tend to be made up of smaller droplets, which leads to them being whiter and therefore having more of an albedo effect. And because they're made of smaller droplets, they last longer in the atmosphere. So you could have gone into quite a lot of detail in terms of describing the mechanism by which the climate will be changed, in terms of what parameter in the model of the surface temperature, in this case the albedo, changed, and then gone in and maybe said some things about where on Earth matters for the volcano to have a big effect. So this is a map of the sulfur content of the atmosphere following the eruption of Mount Pinatubo, which was particularly important or particularly significant for global climate because it was located near the equator. So the aerosols could get into both hemispheres relatively easily, whereas eruptions that happen at high latitudes might have a lesser climatic effect. Another mechanism which which actually is responsible for quite a lot of the variability in the global temperature is related to internal variability within the climate system. So this is these are basically not external forcings, so not really changing any of the parameters in that climate model, we're just redistributing heat from different kind of parts of the Earth, and that can have effect on the surface temperature. So the example given in the lectures was the El Nino Southern Oscillation. So this is where the Pacific kind of switches between two states. That's on the left here, showing where most of the warm water is kind of piled up over on the east. When I say east, I mean of course west. And then an El Nino situation where the water kind of spreads out east across into the eastern Pacific. Now, you could have gone into the mechanisms by which this oscillation occurs, what is causing the water to pile up on one side of the ocean and not the other, in terms of the prevailing wind direction being from east to west. That causes the water to pile up, which causes there to be more kind of warm water over the western Pacific, which causes the air there to heat up and rise, causing a low pressure, which then reinforces the wind circulation, leading to a coupling between the atmosphere and the ocean, and a characteristic pattern of sea surface temperature of slightly cooler in the east, where the water is moving away from, so water from the deeper ocean, which is kind of cooler, can upwell to the surface. And then when that system breaks down, when you have a weakening of those winds, you allow some of that water to start to move back to the east, moving that center of kind of convection in the atmosphere to the central, more over to the eastern Pacific, leading to a reversal of the temperature patterns in the ocean. So that in itself would be great. That tells us all about the mechanisms for what's changing El Nino, but then we need to think about how this actually kind of ends up resulting in a change in the global temperature. Now, this is actually not a done deal. This is still an active area of research in science, but we kind of have explained, how we switch between these two states. How are these things related to global temperature? We covered this in a little bit of detail in the lectures, in that when we have a strong El Nino kind of state in the Pacific Ocean, this is when the warm water is spread out more over most of the central and eastern Pacific Ocean. That corresponds with an average global temperature which is warmer than normal. Okay, so it will be good to point out that when we have El Ninos, we tend to have warmer than kind of normal global temperatures, and we have a La Nina, the global temperatures are suppressed somewhat, and this is partially due to just the surface temperature of the ocean. When we expose cooler water in a La Nina state, where the water is being moved away to the west, that allows more heat to go from the atmosphere into the ocean. It's not quite that simple. There are other teleconnections going on with high latitude areas as well. But important things to note here are that there is a link between the state of the ENSO system, La Nina or El Nino, and global climate, and that is largely related to the transfer of heat between different parts of the Earth, different reservoirs of heat energy. Okay. Right, so that would have been a good thing to have. Go into those things in quite a lot of detail because it's a question that's got quite a lot of credit associated. So quite a lot of people missed out on getting the really high marks in that question, and that's largely because they misdirected their efforts towards kind of things that the question wasn't specifically asking. So that's the thing to watch out Okay, so that is that's done. I think for part B. I'll do another video for part D. Yeah, soon. I mean, when I say soon, I mean it should be done by the time that I put this one on the internet. But anyway, I hope you found that useful. If you're, listening to this next year for revising for next year's exam, that hopefully should be helpful. If you have any questions, discussion forum, email, whatever, you know how to contact me. And if you're not, on the course, then just comment in the comments below, and we'll answer some stuff, hopefully for you. Okay, right, stopping